So hello everyone. Today we're going to be talking about the flow time analysis, which is the topic before the last topic. So we only have two topics left, and this is the first of the two. So last week we talked about a process, and for example, we took the check-in at an airport process, and we said there's customers flowing in, customers flowing out. And we said there is a very important parameter. We mentioned three parameters, R, I, T, and T is going to be basically the time an average customer it takes for an average customer to move from the beginning of the process towards the end of the process. This is T, and this is flow time. So flow time analysis is basically the analysis of T. So that's what we're going to be covering in this presentation. So why do we do flow time analysis? So first of all, the customer is going to value it because customers don't want to spend too long in a process, whether it's a check-in process or maybe doing a banking transaction. If that's the process, also customers wouldn't like to spend too long in it. Also in production, if you have shorter flow time, then it's going to be reducing the inventory needed, and all the different processes that depend on that processes will be relieved. So it's gonna help with all operations. Also, when it comes to product development and design, the faster you could design your product, the faster time to market. And feedback and correction, if there's any corrections or feedback, also it's faster to do it if you have shorter flow time. So in this presentation, basically we're gonna be talking about reducing flow time and the factors managing flow time, and we're going to be really also talking about the critical path in a process or in a system, because the critical path is going to decide which activities should be targeted when we want to reduce process flow time. So as mentioned, we have the flow time and critical path. That's what we're going to start talking about. Then we have the theoretical flow time, which is basically the theoretical flow time is basically the flow time if we weren't to wait, if there was no waiting involved. And then we're going to be talking about tools and how to manage theoretical flow time. So you might remember the critical path from COM 225, where you had different paths and you identified the path which is the longest turned out to be the critical path. So here's an example of a series of activities in a process, and we have two different paths, this path right here and this path right here. If we sum all the times along this top path, we get 5 plus 20 plus 15, so that's 40 minutes, while the bottom one is 30, 35, 50. So right away we know that the longest path is this path right here, which that would be the critical path. So this is the critical path. So in the critical path method, all we're doing is we're identifying the different routes or paths, and the longest path is going to be the critical path. So why is the critical path so important? So let's look at three different paths here. If let's say this path takes 15 minutes, this one 25 minutes, and this one 13 minutes. Now the 30-minute path is going to dictate how long the process is. So if we want to reduce the process time, that's the path we need to tackle. This path is what we need to tackle. The other two paths, if we try to reduce the time on the two other paths, it will not affect the time for the whole process because it would still be 30 minutes. So we care about the critical path because it's the longest path, and it's very important because this is the path we want to concentrate on if we want to reduce the overall process time. So let's do an example on the critical path. So we see this process which has a set of activities, and these activities are right here, and there's a flow time for each one of these activities. So there's a flow time for each one of these activities. Now what we want to do is identify the different paths in this process, and obviously there is this path right here, and then there's this path right here. Now what do we do now is we calculate the length of each path by summing all the different times, which are right here. So let's sum all the difference. So for path 1, we just add up the times, 20 plus 25 and so on, and we get 120 minutes, while the other one we sum and we get 150 minutes. And obviously path 2 is the critical path because it's the longest. It's quite simple. It's always the longest path is the critical path. So the flow time of the process is basically determined by the critical path. So the flow time of the process is 150 minutes because everything needs to wait for that path. So if let's say we have maybe 3 other paths that are not critical, it becomes not important how long they take, because no matter how soon they finish, it will not affect the whole process because the overall process is dictated by the critical path. So the flow time of the process is always the critical path time when it comes to critical path questions. So now that we've done an example on the critical path, we move on to the next subtopic, which has to do with theoretical flow time. Theoretical flow time. And at this point, we want to go deeper to understand what a flow time is. So let's say you're going to do a banking transaction at a bank, and that's the process. So your process is bank transaction. So there is inside that bank transaction, that process, there is some form of waiting time. Whether you're standing in line to do the bank transaction, or even if there wasn't a waiting time and the banking assistant is probably making a phone call to get some information for your banking transaction and so on. All that time is waiting time. So our flow time actually includes 2 things: the activity time plus whatever the waiting time is. Now, so the theoretical flow time is the one without the waiting. So if we were to take flow time and take out waiting, that would be the theoretical flow time. And that would be exactly then equal to activity time. It would be exactly equal to activity time. So the theoretical flow time is exactly equal to activity time, or the time of the process without any waiting or interruption. Sometimes we're interested in knowing what proportion of the flow time is actually due to waiting. That brings us to the concept of flow time efficiency, which basically compares the flow time which include waiting to the theoretical flow time which does not include waiting. So flow time efficiency is basically this equation right here, where it relates the theoretical flow time to the average flow time. So this is a good equation to remember. Remember, your exam is going to be open book, so you could summarize the notes yourself, have them with you when you want to do the quiz and the exam. So this equation is important because it's gonna, so if a question gives us flow time efficiency, then we would be able to find out the theoretical flow time and the average flow time. Or sometimes the question might ask us for the flow time efficiency, and as long as we know the theoretical time and average flow time, and remember the difference between the two is weighting. Right? So the theoretical flow time does not include weighting, while the average flow time includes weighting. So let's do an example on theoretical flow time. Now remember, this is a good time to pause the video and try to do the example yourself. So the flow time for the process is 150 minutes, while the critical path of the process takes 60 minutes. Now, so the critical path, 60 minutes, is the longest path, so the process should be finished in 60 minutes, right? But the fact that it finishes in 150 minutes, basically tells you that there is a lot of waiting in the process. So let's compute the flow time efficiency. So for flow time efficiency, we have this equation right here, where it is the theoretical flow time over the average flow time. So the theoretical flow time is going to be the smallest of the two, because when you take out waiting, it's going to be a smaller number. So it's 60 minutes. While the average flow time is the longest, which includes waiting, is 150. So right away, we identified the different components, all the different ingredients we need for the equation. We go 60 over 150, and it's going to give us 0.4. So the efficiency of the process is 40%. So far we said that the flow time is equal to some theoretical flow time plus waiting. But the theoretical flow time itself is made up of value-added activities and non-value added activities. So even the theoretical flow time in itself is broken into value added adding flow time activities and non-value added flow time. So if we take the theoretical flow time, so if we have 10 minutes theoretical flow time, maybe 2 of these 10 minutes are actually non-value added time, where you're doing something that doesn't add any value from the customer point of view. Now, it's very important to understand the definition that value-added activities is from the customer perspective. It's not from the producer perspective. It is from the customer perspective. So before we go on to talk about the management tool for theoretical flow time, let's just elaborate a little bit more on the difference between value-added activities from the customer perspective and the producer perspective. So for example, let's look at inspection. So inspection might be a value-added activity from the producer point of view, because when you're inspecting product, you're making sure that you're not sending poor product to the customer, which basically means that you have to pay some warranty, you have to ship the product back, and so on. So the producer might think of it as a value-added activity. But from a customer point of view, inspection doesn't add anything to the product. It doesn't make the product any better. It doesn't improve the design of the product. It doesn't do anything of that sort. So when we're doing process mapping, is we basically have to remember the difference. We have to focus on the customer point of view. So if you ever have a question where you have many different processes and you have to eliminate some non-value added processes, you have to think about the customer. Does that process add any value to the customer? Does it make the product better from a design point of view, from a finishing point of view, from a service point of view? If not, then it's not value added activity. So now, what tools do managers have to basically managing theoretical flow time? So, so first of all, is we want to reduce. Obviously, we want to reduce flow time. We said from the beginning it's very important to reduce. So flow time T right here, we want to reduce it as much as we can. And there's many things we could do. First of all, is move work off of the critical path. So we know the critical path is going to take the longest. So try to move work from the critical path to other paths, and that's going to shorten the overall time of the process. Reducing non-value added activities. As we said, the flow time, we have a time for flow time, and part of that is waiting and theoretical, and even the theoretical part of it is value added and non-value added activities. So we want to take out the non-value added activity, or at least reduce them. Reduce the amount of rework. This is very important because rework adds into the overall time of our process. Because we could, if we don't do any rework, we could use those resources to actually work on the process, and especially to work on the critical path. Modify the product mix. Sometimes changing how the product is might reduce the time. Obviously increase the speed of operation is one point, very important point. Crashing resources. We've seen that in COM 225, where when the activities take too long, then we use overtime to reduce the time. So that's an example of increasing the speed of operations. So let's discuss some of these tools. So let's start with moving work off the critical path to non-critical activities. So now if let's say we have, let's draw it in red. Let's say we have, now let's say the red path is the critical path. So the red path is the critical path. So maybe what we, and the green path is not the critical path. So maybe we could take one of these activities and move it to the green path where it's not critical, and then so what we're doing is shortening this path. Or maybe we could remove uh, some of the work in that activity to another path, so it's done in parallel. By doing so, we'll be reducing the critical path. Another way is to actually to use pre or post processing. So maybe before even the path starts, the critical path, we have some time that we could do some of the work beforehand. And this is especially important for projects where the projects have to wait maybe till a certain date for it to start. Well, in that waiting time, you could do some of the activities. So you're done some of the activities which are important, which are on the critical path, you could do them before. In operations, we see this done a lot, where operations in factories, they try to do some work offline, which basically when the factory closes, so maybe during midnight. So if a machine takes a long time to do some form of operations, then you have that machine working overnight. So that's an example of moving work off to pre or post processing times. So reducing the amount of rework, obviously, if the job is done right the first time, then there is no need to do rework. And that's probably the most important method, is to design the process well. So this is why we study processes, and we try to see how they could be done better, so we don't have to do any rework, because rework will cost money. So reducing non-value added activity, and again, these are from the customer point of view. So they're non-value added from the customer point of view. is obviously a good method, because if we could take out all the non-value activities, then we're left out with only value-added activities. So the customer is happy because we're not taking anything that is not adding value, and then it's going to shorten the overall time of the process. Now, value-added activity, customers will value those, so it's good to keep them. Now, the non-value-added activities, the customer does not value them. And example of that, here we give some example of this. Moving workers or work to various locations, so all sort of transportation doesn't add any value. Taking too much time to schedule, setting up machines, sorting, storing, all that is my non-value added from the customer point of view. Now, we have to remember that non-value added activities are non-value added from the customer point of view, but from a producer point of view, some of it is necessary. So this non-value added from the producer point of view, there is some non-value added that does not support the core process, and that could be easily eliminated. Now, the other parts, which is more tricky, is there's some of it is necessary work and could only be eliminated if we redesign the process. For example, if you have a company that has various locations and workers have to move between these locations, then obviously the movement of workers between these locations is very important for the company, because otherwise the work wouldn't be done. Yes, it doesn't add value from the customer point of view, but it cannot be altered or changed unless the whole process is changed. So maybe having everything done in one location, so changing redesigning the process, that would be an example of a way to get rid of the necessary work from the producer point of view, which is non-value added from the customer point of view. Another tool for improving or managing theoretical flow time is increasing the speed of operation. So you just make operations go faster. So if you have a process that takes 1 month to finish, you just increase the resources to speed up operation, and instead of doing it in 1 month, you do it in 2 weeks. So how could we do it? We get better equipment, better technology, or we give incentive for faster work. Overtime could be more manpower, or overtime could be also very popular for increasing the speed of operations. So before we go on to an example, remember that when we increase the speed of operations, that might affect quality. So quality might suffer. So you have to manage quality well while you're speeding operations. Now we look at an example. This is a Montreal traffic court, and we have 200 defendants showing up for trial at 9 in the morning. One day, a sample of 10 defendants. So we have a sample of 10 defendants, and so these are the sample of 10 defendants. And the time spent discussing with a judge and transaction of payment. So each defendant is meeting the judge and speaking to the judge, and then they're spending some time to pay the fine. So this is defendant 2. For defendant 2, spending 1.5 minutes with the judge and 2 minutes paying the fine, and so on. So this is not including waiting time. So the time spent discussion with judge and transaction payment not included were recorded below. Estimate the flow of time of the process. So we calculate how long each defendant spent in the court. So, for example, for defendant 1, he or she arrived at 8:45, left at 9:30. So that's 40 minutes total time spent in the system. So that time is waiting plus actual meeting the judge and paying the fee. So that 45 minutes is the actual time in the process, but that includes obviously a lot of waiting. Only he or she only meets the judge and does the payment for 6 minutes. The rest of the time is just wasted waiting, and so on. So each defendant has similar times. No, not similar time, different times, but I mean the logic is the same. So for example, for dependent 10 arrives at 9, leaves at 9:20, so 20 minutes in total. 1.5 minutes in the judge with the judge, and 3 minutes paying the fine. So we'll take, so the flow time is basically an average. Remember, flow time is an average figure. So we take all these times. So all these times we take all these times and we take an average of them, and that average turns out to be 2 hours. So the average is 2 hours. So the average flow time is 1 hour, 2 hours, which means 20 minutes, 120 minutes, and that includes waiting and actual service time, includes all. So now the theoretical time is a whole different story. But let's just remember what they. So this question asks us to estimate the theoretical flow time of the process. In the previous question, they were asking us about the average flow time, which we've calculated. Now it's asking us to estimate the theoretical flow time. Theoretical flow time does not include waiting. It only includes meeting the judge, discussing with the judge, and paying the fine. So basically, we're only recording these two sets of numbers, and we take an average for spending time with the judge. We get 1.55, and paying the fine is 2.4. So the average theoretical time is basically taking 1.5 and 0.224, and we get 3.95 is the average time they actually get service in the process. So meeting the judge and paying, so it comes up to 3.95. Part C asks us about the flow time efficiency. So the flow time efficiency, since we've calculated the theoretical flow time and the average flow time, then it's just basically the ratio of theoretical flow time over average flow time to get the efficiency. So it's the two numbers we just calculated, 3.95 over 120, and we get a flow time efficiency of 3.3%. So now I'm going to go quickly over the remaining two examples, which are just about the critical path. So here we have this process. Again, when we're going to find the critical path is we add all the activities on each path. So here it's 175 weeks, and here it is 160 weeks. So this is path 1 is the critical path. So we say that's the process flow time. So the process flow time is actually the critical path. So we know that this is the first path is 175 weeks, and the other one is, or the other one will do it in a different color. The other one is 160. Now they're telling us what happens if activity 2 is increased to 40 weeks. Well, it's now at 35. So if we increase it 5 more weeks, we're gonna be at 165. So this path still not critical. It's not gonna change anything. So no effect, because activity 2 is not on the critical path. But imagine if we increased activity 2 by more than 15, because the difference between that path and this path is 15, then things might change. So now the flow, what happens if activity 3 is reduced to 40 weeks? Activity 3 is now at 45 weeks. So if you reduce it by 5, so you move from 175 to 170. So I think this path is still the critical path. And so the overall process time is going to be reduced to 170 weeks instead of 170 weeks. So here's another question now on, again, on the critical path. Here they're not giving us the network, but they're giving us relationship between all these activities A, B, and C, and we have to draw the network. So now if we draw the network, we should get this network right here. So again, we have this network, same idea, and we have two different paths. There's this path right here, and then there's this path right here. This one, by just adding the number, turns out to be the critical path. So this one turns out to be the critical path, and it's 50 minutes. And that's the flow time of the process. The flow time of the process, again, is the critical path. So now they're asking us what happens if activity A is 50% of the time it's repeated. So we take 50% of 15, so we have 7.5 minutes additional time added to the actual process time. And the process time was 50, so plus 7.5, we end up with 57.5 minutes. So that basically concludes this topic on flow time, T, which is basically the analysis of T. Our next topic is going to deal with R, throughput and capacity, and that would be the last topic in our course. After that, we're done all the material.